Today we're going to talk about the concept of Dalton's Law of partial pressures. And so to start us off, I want to just look at a little simulation. Um, Dalton's Law, he has two forms of his law, and what it deals with, instead of dealing with an individual gas like our other gas laws, we're solving for just a single gas's pressure, volume, or temperature given certain conditions. Dalton's law deals with mixtures of gases, which is what we normally encounter if you think about like in our atmosphere. The air that we breathe in oxygen, we breathe out carbon dioxide. The main component is nitrogen. So we deal with mixtures of gases. So what I'm going to do is I'm going to um, place a couple of gases inside this container. And I want you to notice that as these red particles are colliding with the walls of the container, the pressure gauge is registering that the pressure is 0.14 around atmospheres. I'm going to pump some more. So the more particles we have in here, the greater the pressure because there's more collisions. Now I'm going to put a different gas in. This will give us a mixture of gases. So right now in the container we have the red gas, which we'll call oxygen, and it's the only gas in there, so it's a pure gas. But normal conditions that we encounter on a day-to-day basis is a mixture of gases. So I'm going to pump a different variety of gas particles in here. Notice they're a little bit larger. So the blue gas that you see here is now contributing to the total pressure in the container, and the total pressure is being shown here by the pressure gauge attached to the canister. Notice the total pressure is around 1.10 atmospheres. Both gases are contributing to the total pressure, and so we call the red gas, we will call his pressure the partial pressure of gas A, and the blue gas we'll call the partial pressure of gas B. So keep this visually in your mind as we look at our notes today on Dalton's Law of partial pressures. All right, so let me get my ink pen ready. All right, so Dalton's Law, he has two variations of his gas law. And the first one I like to call the summation formula. What he said was when you have a mixture of gases, the total pressure, and we're going to call that P sub T for P total or even P total. Sometimes you see it written as P total. The total pressure is equal to the sum, which means you add it up, of the partial pressures of the individual gases. So if you consider this mixture of gases, the red gas and the blue gas in a container, we have a mixture of gases. Here's the pressure gauge, which would be registering a total pressure. All the collisions between the particles and the walls of the container is what would cause the pressure. Well, Dalton's first form of his law simply can be written mathematically as the total pressure is equal to the partial pressure of gas A, which is our red gas, plus the partial pressure of gas B, which is the blue gas here. Now, in the event that you had 3, 4, 5 different gases, you would just continue this pattern, adding the partial pressures of each individual gas together. So here I have plus the partial pressure of the nth gas, which is N is just another gas in the mixture. This is the first form of Dalton's law. I call it the summation formula. Now, something else that Dalton recognized is that if you have a mixture of gases, the number of moles of each gas is directly proportional to the partial pressure that each gas exerts. Remember that in our gas law formulas, we use N to represent the number of moles. So thinking back to the picture, if you will, or the animation we just looked at, you can write this variation of his law where he said that the moles is directly proportional to the partial pressure of each gas within the same container. That would mean they have the same volume. That would mean they have the same temperature. The only thing that would vary would be their pressure to their moles. That would maybe be different, but there is a direct proportion, a direct relationship between them. So we can write this as the partial pressure of A divided by the moles of A would be equivalent to the partial pressure of B divided by the moles of B, which would be equivalent to the partial pressure of the nth gas divided by the moles of the nth gas. That is also directly proportional if you know the total pressure and the total moles. You only would need to use like the partial pressure in moles of 2 of these situations if you were doing a calculation though. So let's look at an example. And I like to draw the containers here just kind of to visualize. Think back to the diagram in the animation that we used on the opening slide here. This says we have 3 gases contained in a half-liter box at 0 degrees Celsius. So we have 1 mole of neon. So I'm going to put here the moles of neon is 1 mole. It says it exerts a partial pressure of 1.2 atmospheres. So we will represent that as the partial pressure of neon is 1.2 atmospheres. Then we said we have 1 mole of xenon. So the moles of Xe is 1 mole. And it has a partial pressure of 1.2 atmospheres as well. So this is for the xenon, and that's 1.2 atmospheres. This says calculate the partial pressure of 0.5 moles of krypton. So we have the third gas is krypton, and they do tell us how many moles we have, 0.5 moles. And they want us to find the partial pressure of krypton. That's what we're looking for. Also wants us to find the total pressure. So I'm going to make a little pressure gauge here. It wants us to find P total. So there's 2 things we're looking for here, the total pressure and the partial pressure of krypton. Well, in order to get the total pressure, we have to be able to add all 3 pressures together, and we don't have the third pressure, so the first thing we're going to have to find is the partial pressure of krypton. So we're going to use the pressure to mole formula, and I'm just going to use the neon as my reference point. So I'm going to write the formula as the partial pressure of neon over the moles of neon is equal to the partial pressure of krypton over the moles of krypton. So let's plug into this form. This is our formula we're going to use first. Partial pressure of neon is 1.2 atmospheres. And the moles of neon was 1. Partial pressure of krypton, that's what we're looking for. So P of Kr, I'll leave that. You can write it as an X if you'd like to. The moles of krypton was 0.5 moles. So we're just going to solve for X. So we're going to cross multiply here. So that would leave us with 1.2 times 0.5 divided by 1 is equal to the partial pressure of krypton. So you divide that here, you end up getting 0.6, we need that to 1 CP, and we're looking for a pressure that was in atmospheres. So now we have the partial pressure of krypton. So this is one of the unknowns they want us to find. Now we can use the summation formula because we wanted to find the total pressure that would be registered. So we'll call that P sub T. So according to this, the total pressure is going to equal to the sum of these 3 gases added together, the partial pressures. So it's going to be equal to the partial pressure of neon, plus the partial pressure of xenon, plus the partial pressure of the krypton, which is what we just found. Okay, try to erase that just a tad. Okay, so P total is equal to the partial pressure of neon was 1.2 atmospheres, partial pressure of xenon 1.2 atmospheres, and we just found the partial pressure of krypton, 0.6. So you got 1.2 plus 1.2 plus 0.6. When you add, remember, go at least decimal places, so there's 1 decimal place in each of these. That's going to give us our final P total equal to 3.0 atmospheres. Okay, let's look at one final example. Here we have a tank of 3 gases. So again, we have 3 gases in a container. This just happens to be a coincidence. Sometimes you have 2 gases, sometimes you have 4 gases. You can have a bunch of gases in there. Here we have 3. And they're telling us the total pressure. So they're giving us the P total is 16.5 atmospheres inside this canister. It says you have 1 mole of neon. So 1 mole of neon. And they tell us his pressure is 9 atmospheres. So the partial pressure of neon